Hello, here is the lecture, the online lecture for data rejection. I did make it probably halfway through this for the section one, the section that meets at 8 a.m. So if you are in that section, I would recommend watching all of this to help reinforce that. But if you feel you got a really good handle on it, you might want to skip ahead to where we take off from where we left off. Let's get going. We're talking about data rejection. There are three scenarios that we want to look at. The first scenario is that it is never okay to reject data. And essentially this scenario happens when it's a very critical situation, or if it'd be very valuable if we found a positive result, say like you were testing a new cancer drug. If there's one case that looked like that drug helped a cancer patient, then you would want to further explore that. Or also, if it would result in something really disastrous, like the Challenger disaster. Say if you were testing a rocket motor O-ring under, there's some extreme circumstance where it got really cold and it failed, that might not be something you want to throw out. You might want to consider the effects of that when it would actually be used. If they had done that, they could have avoided the Challenger disaster. Scenario 2 would be that the data can be rejected if there's a known experimental problem. So say you have a broken wire, you may have experienced that in lab, you move the wire around a little bit and there's a spike of noise. You might want to just throw that data out and replace that wire. Or say you didn't calibrate your sensor, or say there was an earthquake during an acceleration measurement. Those would all be reasons why you would decide to throw out data. Scenario 3 is the one that we're focusing on for this lecture. And that is that data can be rejected if it's very improbable. You see that one red data point in that figure, that would be an outlier, and there's criteria for should we eliminate that point or not. And that's what we're going to be studying. There are 3 rules for scenario 3. They're all listed here. The exclusion should be used minimally, that is once or twice. If the scatter is bad, if the criteria indicates that we need to delete more than 1 or 2 points, then we should go back and re-examine our procedure or our equipment setup and our calibration. Basically, we need to go back and improve our experiment. And the third rule is once a point has been excluded, we need to recalculate the standard deviation and the mean. And then we essentially go back and repeat the process again. You'll see that in the example that we do. There are many different approaches for data rejection. We have 4 listed here. The 2 that we're going to focus on are the Thompson and Montgomery. Just know there are other approaches. The first approach, the Thompson approach, so here is by the ASME 1998 standard. This approach is what we would use if we're taking many measurements of the same measurement value. So say it's a certain temperature, we're just measuring that many times. So we have xi, with I being the number of measurements. So if we took 20 measurements, we'd have xi. So I would be 1, I would be 2, I would be 3, and so on. The average, or the mean of those, is x bar, and the sample standard deviation is s. So those are the terms we need. And then from that, the first thing we need to do is we need to define the deviations. That's just going to be the absolute value of each of our data points minus the mean. So essentially that's like the random error from one of our early lectures, a theme throughout the course. It's that difference between the value and the average. What we want to do after that is we want to start with the largest deviation. So whichever data point is furthest from the mean. And we want to compare that with the product of the standard deviation and tau. Tau is what we get from a table. It's on the following slide. We're going to get to that in a minute. But we want to compare our deviations to the standard deviation, the sample standard deviation times that tau. And if that largest deviation is greater than that, then we eliminate that data point. And then, like we said back in the rules, we want to recalculate the standard deviation and the mean, and we want to repeat. If there are no deviations that are greater than the sample standard deviation times tau, the data set is fine. So let's look at how we get those tau values. This is the table we use. It's just based on the sample size. So see that as our sample size grows, so we have more certainty that our average is close to the true value, then the tau grows. So the data point needs to be further from the mean to be eliminated. So it's pretty simple. You see how many measurements you made, you find the appropriate tau value in the table, and then you multiply that times the sample standard deviation. And you compare your sample standard deviation, you compare your deviation to the sample standard deviation. Now for Montgomery's approach. So this one is different in that you have like a functional relationship between your xi and your yi. So where Thompson was just measuring the same value over and over, here you're getting a change in y with a change in x. Note here we're getting a clue that point A is the one that we're going to be considering whether or not we can eliminate it. To find out how we do that, the next few slides will show that. Okay, the first thing we need to do is you need to have a line of best fit. You see that here, and then your value of yi, so yi would be your f of xi. You see that kind of upper right-hand corner, f of xi equals axi plus b. That's your line of best fit. That f of xi is yi. So if yi, capital yi, it's a little confusing here. So the small yi, that's your data point. The capital yi, that's going to be your line of best fit. That's going to be your f of xi. See, capital yi, that's the value of your line of best fit at a particular x. And then yi, this is the value of your measurement. So the error, this ei, the difference between these, or in other words, your residual, that is just subtracting your f of xi or your capital yi, or subtracting small yi, your data point, from that f of xi or capital Y xi. Find that difference between your line of best fit and your data point, and that is your error or your residual. So you get that, and the next thing you need to do is calculate your standard error of the estimate. And here is the equation for that. So it's a root sum square type of thing. Here are those residuals. You square them, you sum them. You need to divide that by the number of samples minus 2, and then you take the square root of all of that. And then the next thing is to standardize the residuals. So you're just dividing them. You divide your residual by that standard error of the estimate. It's kind of a normalization process. Then the criteria for whether we keep that point or not is we keep it if that normalized residual is greater than -2 or less than 2. Essentially, that stands for 2 standard deviations, plus or minus 2 standard deviations. 95% of data lies within those. So essentially, we're keeping it if it's within 2 standard deviations. We're keeping 95% of data. And if it's outside of that criteria, so if it's less than -2 or greater than 2, or as we've written it here, if the absolute value is greater than 2, or in other words, it's outside of 2 standard errors, then we eliminate it. So here's a question for you. When using Montgomery's approach for outlier rejection, what do you need to calculate? A, linear regression coefficients, B, the residuals, C, the standard deviation, D, the standard error of the estimate, or E, A, B, and D. I'll pause for a second to let you think about that. The last few slides, if you want to go back in the video, they would show that we need to calculate A, B, and D, but not C. So the best answer would be E. Now here, we're showing an example of how we use Montgomery's approach to determine if any outliers should be rejected. So we have our X and our Y data. We have this functional relationship between them. We plot that out. We likely use Excel to get a line of best fit. We plot that function up here. And then we have, so we have a function for, here's Y prime. This, on the previous slide, would be your capital Y, the subscript, or it would be your f of x. A subscript for, which x value we're calculating for. And notice your r squared, your correlation value here is 0.65. So that's pretty low. We have quite a bit of scatter here. Now we'll come back to that, but let's look. So we take this equation and we enter our x values. So we get our, in this case, y prime. Other notation we saw was the capital Y or the f of x, all the same thing. So here we're getting that for each of our x values. It's just plugging those x values into our line of best fit. So get all those, and then the next step is going to be to find the residuals. So you just subtract y from y prime. We get these values. And then the next thing that we're going to need to do is to calculate that standard error of the estimate. We use that equation below. If we did that, we would get 22.15. The next step is going to be to normalize. So it would take each of those residuals and divide it by that standard error of the estimate. That's that new column there that was added. We see this shifts the data over here. It's all normalized to this 0. The distance from that is showing how far we are. So how many standard deviations essentially we are from that mean value. And now we just use that criteria of is it less than or greater than 2, that largest deviation. And here we're seeing data point 8, or for an x value of 8, that normalized ratio of the error to the standard error of the estimate is greater than 2. So we should reject that point. Then once we reject that point, we recalculate the regression. We'd eventually repeat all the steps, but let's just look at the result of recalculating that regression with that data point eliminated. And you see now our R-squared value went up to 93%. That's a big improvement, eliminating that point. We could go on from this point to see if any other points should be rejected based on that criteria, but there aren't any. That's it. Have a good day.